Okay, grade 11, this thing is though we are done with all the theorems, at least going through what each theorem says, and then going through the diagram, and then going through problems related to the theorem. We can now sort of like get a sort of overview of the respective theorems, but also let's get our heads now into problem solving mode to solve what we call riders. We call these riders, where you have a particular problem that you have before you, and there's a mix of different theorems in that particular problem, and you need to find angles, sides. Sometimes you need to find unknown angles, you need to find unknown angles in terms of other variables, proving cyclic quadrilaterals, proving if they are tangents, proving that their lines parallel, and so forth. So we're going to start diving into something of that nature. So now there is a skill set that we need to have whenever we are approaching these problems, and I want us to actually go through line by line what it is that we need to do whenever we are approaching riders. So the first thing we need to do is read. Every rider has a statement that is accompanied by the diagram. So the statement that is written above the diagram, that is what we need to read. We need to read, and read. And we need to read with a little bit of comprehension of what it is we are reading and how it relates to the diagram. So we need to read the info next to the diagram, and we need to do that thoroughly, okay? Then 2, after reading the information in the statement, we then have to transfer all the given information from the statement to the diagram. Sometimes the diagram has the information that is provided in the statement, but oftentimes some of the information in the statement may not be explicitly visible in the diagram. Okay, right. Then 3, we need to look for keywords. Example, the word tangent, all right? The word tangent should remind us of the theorems that we have done. So for instance, the minute you see the word tangent, you should be able to call to memory tangent perpendicular to radius. You need to be able to call from memory tangents from the same point are equal. And then you need to also call from memory the theorem that says the tan chord theorem. Okay, so whenever you see that word, visually you need to see these theorems represented in your mind. Okay, which is why we spent a bit of time looking at these theorems individually, so that you guys can familiarize yourself with the diagram and also with the accompanying reason for each theorem, and what statement is actually derived from the theorem and its accompanying reason. Okay, moving right along. Cyclic quadrilateral. By that we need to know the properties of the cyclic quad. All right, now obviously there are 3 essential things that we need to know as far as properties of cyclic quadrilaterals are concerned, and that is 1, the opposite angles of a cyclic quadrilateral are supplementary. Okay, 2, the exterior angle of a cyclic quad, meaning T1, is equal to the interior opposite angle of the cyclic quad, meaning angle T1, which is exterior to the cyclic quad, is actually equal to angle R, which is the interior opposite angle. Then lastly, the fact that angles in the same segment also infers cyclic quadrilateral. Okay, angles in the same segment, the fact that angle X is equal to angle Y. Okay, so that's very important too. Then this important truth, and that is you never must assume anything. All right, and that is, don't assume a certain line is a diameter. Okay, you'll remember that a diameter is a line that passes through the center of a circle. So it might look like, when you look at the diagram, okay, remember diagrams are never drawn to scale, but it might look like that a particular line, which is a chord, is a diameter, because it kind of looks like it passes through a particular center, because it's midpoint of the circle. But please, we need to never assume. All right, Rather, don't assume a certain line is the diameter of a circle unless it is clearly stated or unless you can prove it is a diameter. Okay. Next, don't assume a point is the center of a circle unless it is clearly stated. Now, they have various ways of being able to sort of allude that something is the center. For instance, if they say circle M, and what you'll notice is that if they say circle M, you'll find that in the center of that circle, the letter M is clearly there. So if they say circle M, that means that the circle has a center, which is denoted by the letter M. So it means circle with midpoint M. Does that make sense? I hope that makes sense. Then we need to be able to generate something called the grocery list with reasons. Now the thing is, when you look at a particular diagram, you should be able, as you look at it, immediately, because you know your theorem so well and you know the diagrammatic representation of each theorem, you should be able to immediately see that, oh, that angle is equal to that angle, and for a particular reason. All right. The question that may come after reading the statement and looking at the diagram may not necessarily be asking you to prove that that particular angle which you are seeing is equal to what you are being asked in the first question. But you may find that as you go through the diagram itself, and as you sort of like a grocery list, start writing down the items or the theorem the statements that you see from the diagram with their accompanying reasons, based on what you can just generally see, and you start writing those statements on the side with their reasons, and you collect them, then that may be able to set you up for when you start answering a particular question, because you may find that some of these generated lists of yours, your statements and their reasons, may be used in being able to answer some of your questions as you go along. Then, very important, mark all equal angles with the same color. So you have the liberty of being able to bring your colored pencils there so that you can be able to mark equal angles with the same color. That's if that will be of benefit and help to you. So for some people, generating grocery list may not be something that's necessary, but it may be necessary for some people. So that's a skill you can adopt that can assist you in your way to answering questions. Also, lastly, marking all equal angles with the same color. That may be something that may be helpful for a learner who probably would be able to derive a whole lot more from the diagram if they used different color pencils to be able to identify equal angles. So these are just things that you can do as you go along, but essential things, of course: reading, transferring information, looking for keywords, very key. Never assuming that anything is something unless you can see it stated in the statement or you can prove it otherwise. You know, that goes for diameters, that goes for anything. And don't assume that a point is a center, you know. And then these last two, like I said, may be beneficial for some learners and not for some others. So you do what you feel is best, okay? So I just wanted to bring to our attention the theorems that we have covered so far. So in our memory bank, these theorems should now be in our heads. So you have what I would say, as we group them, we have what we know as our center theorems, okay? Our center theorems are that theorem that says a line from the center perpendicular to the chord. What does it do? It bisects the chord, all right? And obviously what we would say here, let's say if we had O, B, C, D, what we could say here as the statement is we could say BC is equal to CD. The statement is something unseen from the diagram. The reason, on the other hand, is something that we explicitly see from the diagram. So BC is equal to CD is something we can conclude based on the diagram. And the theorem statement that says a line from the center perpendicular to the chord, what does it actually do? It bisects the chord. So in other words, we can say BC is equal to CD, and this is our reason: line from center perpendicular to chord. And this is according to the acceptable reason document that we have. Then let's look at this theorem. This one is the one that says a line from the center to the midpoint of the chord. Why do I know that's the line from center to the midpoint of the chord? It's because I can see these two equal this is the midpoint and these two are equal. So let's say this was BCD. So let's say that was O. So we can conclude from this diagram, we can conclude that OC is perpendicular to BD. Or we could say, in other words, OCD is equal to OCB, which is equal to 90 degrees. What would be our reason? Our reason would be line from center to midpoint of chord, right? So this statement, unseen from the diagram, we are stating it based on what reason? The reason is line from center to midpoint of chord. And you can see we shorten midpoint to be MIDPT. So this is according to the acceptable reason document that we have. Okay, those are two theorems revolving around the center. There's another center theorem, the one that says angle at the center is 2 times the angle at the circumference. Now it's very important to note that that theorem has something to do with the fact that if an arc of a circle subtends an angle at the center, that angle that is subtended by the arc at the center is equal to 2 times the angle subtended by the what? By the same arc, you see, at the circumference. So this is the angle at the center, angle at the circumference. So we would say here AOB is equal to 2 times what? ANB. Reason, angle at center is equal to 2 times angle at circumference. Same thing here. This applies for this diagram as well. I've drawn it accordingly. The angle that we are talking about here is AOB, the reflex angle, not the angle inside, but the angle external to the diamond diagram. This is the arc AB. It subtends this angle at the center. That same arc subtends the angle at the circumference. Okay. Moving right along to the third diagram, which also represents angle at the center as 2 times angle at the circumference. This arc AB subtends this angle at the center, angle AOB, which is equal to 2 times the angle at the circumference. The same arc subtends another angle at the circumference. So this angle at the center, AOB, is 2 times the angle at the circumference. Okay, so all 3 of these diagrams fall under angle at the center is equal to 2 times the angle at the circumference, and they are also center theorems. So the minute you see center or radius or diameter in your diagram, then of course it should call to memory these theorems, all right, their diagrams, all right, and remember the reasons, or this last one, which basically says angles in a semicircle. In other words, a diameter subtends 90 degrees at the circumference. Now obviously this is just something that you can conclude, but the 90 degrees is not there. We all know that if this is a diameter, meaning it's a line that comes from one end of the circumference to the other, passing through the center, and you can see that that diameter, as per the triangle, this entire diameter subtends the angle C at the circumference. Then that angle C that it subtends at the circumference, we say angle ACB is equal to 90 degrees. What's our reason? Angles in semicircle. Angles in semicircle. Or we can say diameter subtend right angle. Very important. Diameter subtend right angle. Or we could say angle in half. Then we write the circle with a dot inside. So one of 3 of these reasons are acceptable. According to the acceptable reason document, you can use them to basically state that the angle ACB is equal to 90 degrees. Hope we are together. Then here's another center theorem. The next center theorem is this one. Here you can see center O. You have A there, you have C there, you have B there. Something we can conclude very easily is that AO is equal to CO, which is equal to BO. Reason? Radii. We say that the radii are equal. One radius, many radii. All right? Plural. Okay? So that is specifically in reference to the center. Okay? Then we can move on to the next keyword, and the keyword is cyclic quadrilateral. In cahoots with cyclic quadrilateral, they could use the word concyclic. Concyclic basically also means 4 points on the circumference of a circle. 4 points on the circumference of the circle, like NMST, without actually stating that it's a cyclic quadrilateral. They could say NMST are concyclic. What does that mean? It means it's a cyclic quadrilateral. Okay, so these are the keywords, key points. And then the minute they say that, what should come to our memory? 3 things. The fact that opposite angles of a cyclic quadrilateral, remember all 4 of these points are on the circumference of the circle. So that means opposite angles of a cyclic quad. Angle M plus angle T is equal to 180 degrees. Angle N plus angle S is equal to 180 degrees. Very important, that thing, okay? Very, very important. The reason we use opposite angles of a cyclic quad, and this is per the acceptable reason document. Then we have exterior angle. In other words, the line that is external, that leads to the external angle, must be in line with the side of the quadrilateral that we are speaking about. So since TS continues, extends to TU, then external to that we have angle T1. That means angle T1 is equal to angle R. Why? The exterior angle of a cyclic quad is equal to the interior opposite angle. So this is the acceptable reason. Exterior, ext, small letter E, we actually use there. Angle of cyclic quad. Done. Then we should think of angles in the same segment as well. Okay? In other words, WXZ, angle WXZ is equal to angle WYZ. Reason? Angles in the same seg. Okay. All right. So, like I was saying, guys, moving right along, there's also like your accompanying corollaries that are derived from angles in the same segment. You need to know these as well because they speak to equal chords, equal angles. That is also an acceptable reason from the acceptable reason document, and that speaks to the fact that if you have chords that are equal, so obviously that's a chord, that's another chord for 2 respective triangles. But if you have chords that are equal, they subtend, okay, because a triangle will subtend that angle there. This triangle will subtend that angle there. So that means if the chords are equal, then the angles that they subtend at the circumference are also what? They are equal. So that's why it speaks to equal chords, equal angles. This here as well. If you have equal chords within one circle, they subtend the same angles at the center. So we have equal chords that subtend equal angles at the circumference, then you have equal chords that subtend equal angles at the center. And basically equal chords, equal angles is the same reason we use for whether we are talking about equal chords subtending equal angles at the circumference or equal chords subtending equal angles at the center. Then we have one that speaks about 2 circles that are exactly equal or identical. So 2 equal circles may have respectively a chord, and you can see a chord AB is equal to chord DE. There's an angle that this chord subtends at the circumference in this circle, and there's a angle that this chord subtends at the circumference for this circle. But these 2 circles are exactly equal and identical. So we say that equal chords subtend equal angles at the circumference of the circle. So for 2 circles that are equal, the equal chords will subtend equal angles at the circumference. So we can conclude and say B angle, let's say angle B1 is equal to angle C2. What's the reason? Equal circles, equal chords, equal angles. This is the very same theorem that also speaks about the fact that if you have equal chords for equal circles, they subtend the same angle at the center, right, as well. And this is the same reason that is utilized for that particular corollary as well. Okay, so yeah, so this is all that we should think about under cyclic quadrilaterals. Those theorems should come to mind, you know, they should be occupying the upper uppermost part of our minds so that we do not forget them. I think in the same way that someone can be crazy about someone, it's the same way that we need to be crazy about these theorems so that we can be able to remember them. Then there's the tangent theorem, right? The tangent theorem, the theorems that appear under tangents, all right? Keyword being tangent, or if a line touches the circumference of the circle external to the circle, then basically we know that that speaks of tangent. Then we have these theorems. The fact that a line from the center to the circumference that basically touches a line that's external to the circle, that touches the circumference at the point where that line touches the circumference at the point of contact, we say that angle M1 and angle M2, they are equal to 90 degrees. Reason? Tangent perpendicular to radius. So you could say angle M1 is equal to 90 degrees. Reason? Tangent perpendicular to radius. Then the other tangent theorem speaks about the fact that when you have two tangents, all right, that are from the same point S, for instance, two tangents from the same point, we say that those two tangents, they are equal, all right? So we could well say PS is equal to SR, and the reason is tans, all right, from the acceptable reason, tans from common point, or we could say tans from same point. Either one of these reasons is fine, okay? Then we have the tangent chord theorem, all right? As you can see here, tangent chord theorem speaks about the fact that if you have a chord and then you have a tangent, and there's an angle formed by that tangent and that particular chord, then the angle formed by the tangent and the chord is equal to the angle in the alternate segment, or in other words, is equal to the angle that is subtended by the very same chord, all right? It's equal to the angle subtended by the very same chord. So angle S1 is formed by chord SB and this tangent. That's angle S1. That angle is equal to angle P because it is the angle subtended by the chord SB. Then you could look at also angle S2, which is this angle here, that is formed by chord PS and the tangent. The angle S2 will be equal to angle B because it is the angle subtended by the chord PS. Okay, so we'd say S2, angle S2 is equal to angle B, or we could say angle S1 is equal to angle P, and our reason would be tan chord theorem. Okay, that's for an acute angle triangle within our circle, and this would speak about our obtuse angle triangle in the circle. All right, so once again, we got a tangent, we got a chord, and this angle S1 would be equal to angle P because it is the angle subtended by this chord. Angle S2 would be equal to angle B because it is the angle subtended by chord PS. Tan chord theorem. All right, and then just for the tangent perpendicular to radius, you know that the radius can be extended all the way to the other side of the circumference that it forms a diameter. So obviously angle M1 and angle M2 would be equal to 90 degrees. Reason, tangent perpendicular, not the radius but the diameter. Okay, it's kind of like the same theorem but along the same lines. Now we need to also recap and remember what we did in grade 8 and 9 when it comes to proving lines that are parallel. Okay, just before we get into sort of like the nitty-gritties of those theorems. But there are times when we are asked to prove, okay, questions that relate to proving. So, for instance, the question will say, prove that AB is parallel to CD, for instance. So whenever we are asked this question, we need to look at these three conditions that need to be there in order for us to conclude that lines are parallel. So for instance, if I look at this diagram, okay, maybe the question would ask, prove that AB is parallel to CD. And you look at this and you're like, AB and CD being parallel, so diagrammatically it doesn't look that way, that they could be parallel. But you know what? There are certain conditions that could actually, that we could meet, which would basically then help us conclude that AB is parallel to CD. So in other words, if you look at angle, this angle, angle BTS, which is 30 degrees, and you look at this angle, angle SCST. These two angles are both equal to 30 degrees. And their position, all right, gives us the Z shape for who? For alternate angles. So their position says these are alternate angles. When alternate angles are equal, we can then conclude the following. Okay, so BTS is equal to CST, which is equal to 30 degrees. Now that is clearly given, all right? Therefore, AB is parallel to CD. And maybe you're going to be asking, how can I then conclude that AB is parallel to CD? It is because the alternate angled positioned angles, the 30 degrees and this 30 degrees, those two angles are actually equal. Therefore, I conclude and say alt angles equal. You may have wondered, where do we ever use this reason of alt angles equal? We use this reason of alt angles equal to prove that lines are parallel. So if alternate angles are equal, then we can conclude that the lines of Z, the lines of Z, which are supposed to actually be flowing in the same direction, but they are not in this case. But because these angles are equal, the angles that are in the alternate position, we say that AB is parallel to CD. Why? Because these alternate angles are actually equal. All right, I hope that makes sense. Look at this diagram. What if we were asked the same question? Prove that AB is parallel to CD. So we could also look for, if you look at this 20 degrees, it is on top of this line, and on the same side of the transversal line, this 20 degrees on top of this line, these two angles are equal. My F shape, all right? On top, F shape. On top, F shape. Bottom would also be F shape, but it must be on the one side of the transversal line. So I can then say the following. I can then say, let's just say this is M, the line ends at M, let's say it ends at L here, right? I could say ASM, angle ASM, is equal to angle CTS, which is equal to 20 degrees. And I can see that these angles are in the corresponding position because they form my F. Therefore, I conclude that AB is parallel to CD. Why? It's because my corresponding angles are equal. Corresponding angles equal. Hence this reason. That's in the acceptable reason. Okay? Because it does state that if corresponding angles are equal, then lines are parallel. All right? Then last but not least, let's look at this one. All right? Now, I just want to use co-interior angle supplementary to prove that MP is parallel to NR. Ask the same question, prove that NP is parallel to NR. So I'm going to try and use the third condition. Okay, I've already seen how alternate angles equal can help me prove that lines are parallel. I've already seen how corresponding angles equals can help me prove that lines are parallel. And now I just want to also check out how does co-interior angle supplementary prove that lines are parallel. So I know this 30 and this 30 give me that alternate angles, and I could use alternate angles are equal to prove that those lines are parallel. But let's just take it up a notch. NSR is a straight line. Okay, so what I'm going to do is I'm going to find angle TSR. So TSR, we'd all agree, is equal to what? 150 degrees. Why do I say TSR is equal to 150 degrees? It's because angles on a straight line. Okay, that's from the acceptable reason document. Angles on a dot line. And why did I say TSR is equal to 150 degrees? It's because angles on a straight line are supplementary. 30 and plus what gives me 180? It's 150. Now, if I look at the 150 that I've just found, because I always update my diagram after I'm getting an answer, you can see, guys, that this 30 and this 150. They form my U shape. My U shape for co-interior angles. Now, what about these co-interior angles? They are 30 plus 150 gives me 180. Therefore, I can conclude and say PTS, angle PTS plus angle RST is equal to 180 degrees. All right, because I have those angles there. Therefore, no, because PTS is 30 and the RST is 150. Those two give me 180 degrees. Therefore, I can conclude MP is parallel to SR. What's the reason? Co-int angles sup. In other words, co-interior angles are supplementary. All right. So this is basically, guys, something we need to note, that whenever we're asked to prove lines are parallel, we need to check if can't we find alternate angles that are equal. Okay, can't we find corresponding angles that are equal? And can't we find co-interior angles that are supplementary for the lines that we are basically being asked to prove are parallel? Okay, remember, they don't have to look like they're parallel. All we need to do is check if these conditions are there, and that's very important. What about proving cyclic quadrilateral? So if you're proving a cyclic quadrilateral, prove that a particular quadrilateral, a four-sided shape, is a cyclic quad. So there are three conditions that we can check, and that is: one, we can either prove that opposite angles of that quadrilateral, because this is a quadrilateral, are supplementary. If we can do that, in other words, we can prove that this angle B and this angle D both add up to 180 degrees, then ultimately we can conclude and say ABCD is a cyclic quadrilateral, and our reason would be opposite angles quad supplementary. Okay, opposite angles quad sup. Or we could use converse opposite angles of cyclic quad. So any of these two reasons are fine for this first case. The second case would be proving that the exterior angle of that quadrilateral is equal to the interior opposite angle. So if in some way I can prove that angle D1 and angle A are equal, then I can conclude and say ABDC is a cyclic quad. Reason: exterior angle equal ext angle equal int op angles. Or I could use converse exterior angle of cyclic quad. Last but not least, you can also prove that BCDE is a cyclic quad if you can prove that this angle and this angle are equal. All right, or if you can prove that that angle and that angle are equal. You would then conclude and say BCDE is a cyclic quad. Reason: line subtend equal angles. Line subtend equal angles. Or you could say converse of angles in the same seg. Right? So hopefully these three conditions, you know them well, because always when you're asked to prove cyclic quad, you should check: can I prove this one? Can I prove this one? Can I prove that one? All right. Then last but not least, proving a tangent. There are two conditions that you must check, and that is, you must check converse of tangent perpendicular to radius or tangent perpendicular to diameter, or you can check converse of tan chord theorem, or you can say angle between line and chord. All right. If you have any questions, guys, please drop me something in the comment section. I'd be happy to answer those. And if there's a video that you'd like me to do, it's maths oriented on Euclidean geometry for grade 11, I'd be happy to do that. All right. I'd be happy, very happy to do that.